The first elementary signal we study is the unit step function u of t. It is defined as a piecewise function. U of t equals 1 when t is greater than 0 and 0 when t is less than or equal to 0. Graphically, it is flat at 0 for all negative time, then jumps instantaneously to 1 at t equals 0 and stays there forever. This sudden jump makes it ideal for modeling signals that switch on at a specific moment, like flipping a switch. The value at exactly t equals 0 is sometimes debated, but we will use the simpler first definition, where u of 0 equals 0. Now let us compare the continuous time and discrete time versions side by side. For continuous time, u of t is a horizontal line at 0 for t less than 0, with an instantaneous jump to 1 at t equals 0. For discrete time, u of n equals 1 when n is greater than or equal to 0, and 0 for negative n. In the stem plot, we see dots at 0 for negative n and dots at 1 for n equals 0, 1, 2, 3, and so on. Notice that the dt version has no ambiguity at n equals 0. It simply equals 1. The second elementary signal is the unit ramp function r of t. It equals t when t is greater than or equal to 0, and 0 otherwise. We can write this compactly as r of t equals t times u of t. Graphically, it is flat at 0 for negative time, then rises with slope 1 starting at the origin. The ramp is the integral of the step. R of t equals the integral of u of tau d tau from negative infinity to t. Conversely, the step is the derivative of the ramp. U of t equals dr of t dt. This derivative integral relationship will become very important when we study the impulse function. Comparing continuous and discrete ramp functions. For continuous time, r of t is a straight line with slope 1 for t greater than or equal to 0. For discrete time, r of n equals n times u of n, which gives us the values 0, 1, 2, 3, 4 at n equals 0, 1, 2, 3, 4. The stem plot shows these linearly increasing values. Just like in continuous time, the dt ramp is the running sum of the dt step. R of n equals the sum of u of k from k equals negative infinity to n. We can shift both step and ramp functions in time. A delayed unit step, u of t minus t0, switches on at t equals t0 instead of at the origin. For example, u of t minus 2 turns on at t equals 2. An advanced step, u of t plus 3, turns on at t equals negative 3. The same logic applies to ramps. R of t minus t0 starts ramping at t equals t0 with slope 1. These shifted elementary signals are building blocks for constructing more complex signals. Let us build a composite signal. Consider y of t equals u of t minus 1 plus u of t minus 2. The first component, u of t minus 1, is a step that turns on at t equals 1. The second component, u of t minus 2, turns on at t equals 2. When we add them together, we get a staircase. Y of t is 0 for t less than 1, 1 for t between 1 and 2, and 2 for t greater than or equal to 2. By adding more shifted steps, we can build any staircase pattern. For example, adding u of t minus 3 gives us a 3-level staircase. Let us recap. The unit step u of t switches from 0 to 1 at the origin, while u of n does the same at integer n equals 0. The unit ramp r of t rises linearly with slope 1, and r of n increases by 1 at each integer step. Both can be shifted in time to create delayed or advanced versions, and by combining shifted steps, we build staircase signals. In the next lesson, we will meet the most important elementary signal, the impulse function delta of t.